Hi again, everybody. It's good to have you with me today. We're going to complete 4.2 on solving compound inequalities. Now, the first area of compound inequalities that we looked at in the prior video was a conjunction, or solving conjunctions. Those compound inequalities that are joined by the word and. And we showed in that section that a compound inequality can either be written with the word and shown in it, or it is able to be written in compact form. And I think the other thing that we pointed out about conjunctions, those that are involving the word and, is that when we graph the solution of a compound inequality that happens to be a conjunction, the graph is ordinarily a situation to where all of the real numbers are coming together on the graph. Now we're going to move to the second type of compound inequality that happens to be called a disjunction. A disjunction is a compound inequality that is joined by the word or. So up here on this board, just for a second, it speaks to that word. We're going to be turning our attention now to solving compound inequalities using or. And they're called a disjunction. And before we take a look at actually solving a disjunction, we want to look at a prerequisite item that once again is dealing with set theory. And that set theory concept for a disjunction is called the union of sets. So we're going to come over to this sheet of paper right here for just a moment and speak to the fact of what we mean by the union of two sets. And here's what it is. The union of sets A and B, written A union B. Now I'll hold my finger right there to that symbol. It's a U, and it stands for union. Recall the other one where we had the hump, that stood for intersection. But this stands for union. So the union of sets A and B, written A union B, is the set of elements that are members of set A, or set B, or of both sets. In other words, if we are given two sets, the union of those two sets will either be the members that are in one set, or the members that are in another set, or the members that are in both. Union means items coming together, let's say from two different sets. So let's take a look at number one, and let's form the union of these two sets. The easiest way to form the union of two sets is to look at the first set and write down all of the elements that you see in that first set. We'll write all of those down in this device that's going to show our answer. We're going to take all of the members of this first set, so that would be the set whose members are, I got to write a little bit small here, 3, 4, 5, 6, 7, and we're going to join to these elements any uniquely different elements that are found in the second set. Now, we're not going to write 3 again because it was already found in the first. And we're not going to write 7 again because it was in the first. But we are going to write the members 8 and 9 that are in this set. And there is your brand new solution set that has been formed by the union of those two. We're taking all of the members of one and we're joining them with all of the uniquely different members of the other set. Number two, the union of these two sets. We're going to take all of these. That's going to give us the set whose members are 0, 1, 3, 5. And we're going to unite these with any uniquely different ones in this second set. And these are all uniquely different. They're all even. There aren't any even in here. So we'll just join the 2, the 4, and the 6 with what we already had. And there's the union of the two sets. In other words, folks, we're taking everything. We're not going to repeat an element, but we're going to take anything. The union of the set whose members are the letters that give us the word empty, and we're going to perform the union of that set with the set that does not have any members in it at all, the empty set. Well, if we're going to form the union of empty with the symbol for an empty set, we're going to take all of the members that are in that first set, because we're going to join together the elements of this set with the elements of this one. There are no elements of this one, so we're just going to take empty, and that would be the set whose members are E, M, P, T, and Y, and we would have our union. All right, now back to the concept of what our target objective is today: to be able to solve a disjunction. Let's just take for a quick moment, let's look at this little simplistic disjunction. How do we know that it's a disjunction? We see the word or. Folks, that has to be memorized. Compound inequalities that are joined by the word or are called disjunctions. So this one is saying x must be any real number that is greater than or equal to 3, or x can be any real number that is less than 0. You see, people, that the word or indicates that we can take all of the real numbers of x that will satisfy this inequality, or we will take all of the values of x that will satisfy this one. We are not interested in common solutions. Common solutions would be a conjunction joined by the word and. But if it's joined by the word or, it's called a disjunction. So let's look at its graph, because this one has actually already been solved. Let's take a look at x is greater than or equal to 3. X can be 3. That's why I put a bracket there, opening to the right. X is able to be 3 or any number greater than 3. So this is a portion of our graph right here. Or x is less than 0. Or x can be any number that is less than 0. So we put a parenthesis right through 0, we project it less than 0, and we shade the number line in a negative infinity direction. And this would be the graph of this disjunction. And folks, while Kristen is maybe holding that camera right on this graph, this that you're looking at right here is the typical, it's the common looking graph of a disjunction. You see the prefix dis, D-I-S. I remember looking it up some time ago, I believe in Webster's dictionary. And one of the entry definitions for the word dis was separated or apart. The parts of this graph are separated from one another. they are apart from one another. Notice, they're going away from one another. They're not coming together like the typical conjunction. They're moving away from one another. Now, am I sitting here today saying that the graph of a disjunction will always be that look? No, but most of the time it will. But we'll see an occasion, maybe on the exercises today, where it might not quite look like that, but that is the typical look. Now, if we take this solution that we see graphically and write it in interval notation, this is what it would look like. If we were to look at this portion of the graph first, this portion, the largest value of this portion is 0, even though it doesn't count. And the smallest value is negative infinity. So over here, you'll notice I put a parenthesis here, and a parenthesis here, and I put as the largest value 0, and the smallest, negative infinity. People, this portion of the interval notation right here is for this portion of the graph. Then it's either writing the word or oftentimes we'll write the union symbol. So we're going to form the union of those real numbers with the other. And the other, it begins at 3 and it counts. 3 is the smallest value of this interval, and the largest value is the positive infinity, and there you see it. So when we solve the disjunctions today, we're going to solve them, get it down to this point, so to speak, and then show the graph and show the interval notation. Let's go to number 1. 3x minus 5 is less than or equal to negative 2, or 10 minus 2x is less than 4. Solve this first one. Positive 5, positive 5. 3x is less than or equal to 3. Don't have to reverse. Coefficient is positive. Over 3, we'll get x is less than or equal to 1. Then I'll bring down that word or. And now let's come over to this one. We got to get rid of the 10 first. So we do its opposite. Negative 10, negative 10. Negative 2x is less than negative 6. Now we're going to have to divide both sides by a negative 2. And because we're dividing by a negative, we're going to have to reverse that inequality symbol. So I'm not going to put the fraction bar there. I'm going to bring down the negative 2x, divide it by negative 2, and now we'll reverse. Is greater than negative 6 divided by negative 2. And I'll put this other portion of our solution right about here. Or x is greater than 3. So now we ordinarily have the solution. Now let's depict the graph. Let me kind of put it right up here. I don't have to move too much then. Let me just kind of show it right up here. We'll just make a number line. And there's 3 focal numbers that we're going to want to put. We want to put 0, but before I put that 0 up there, look at this endpoint for the first part of our disjunction answer, and look at that one. They're both positive numbers. So I'm going to tend to maybe put a 0 right about there, and then show 1, and then down yonder a bit, show 3. And if the red will come through, on the one hand, x can be less than or equal to 1. So we come to the 1. And right through that tick mark for positive 1, we're going to make a bracket because the equal sign is attached. And the bracket is got to open to the left, moving less than. So put that bracket very definitively there. Opening less than, shade. Or x is greater than 3. Come over to our new endpoint of 3. There's no equal sign there, so it's going to be a parenthesis, and the parenthesis is going to open to the right, greater than. So it's going to open to the right, and we'll shade that. And there is the graph. And if I can just erase that little area right there, let's show our interval notation. Let's pick up this part. You bring down that square bracket exactly in that way. We'll put a parenthesis on the other end, a comma. Put that positive 1 there because it's the larger value of that interval, and negative infinity on the other one. Then a union symbol, and we'll go to this piece. A parenthesis, and another parenthesis. Next to this parenthesis, the smallest value of this interval, 3, comma, positive infinity, done. Now there's number 1. Now folks, I'm going to erase everything so I have plenty of space. The red never wipes away like you want it. Hope you were able to kind of see the things as we were doing. Put those glasses on for a bit and let's go to number 2. X minus 2 is greater than negative 3, or 2x is less than or equal to negative 6. Disjunction. Or, let's solve this first one. Positive 2. Positive 2. X is greater than negative 1. Or, over here, over 2. Over 2. Or x is less than or equal to negative 3. So we have the ordinary solution right here. Now I want you to take a look at this particular one as we do it. Let's show the graph. Let's stick a 0 maybe right about here. Take it out to a negative 1. And take it out to a negative 3. And let's see what this graph kind of looks like. On the one hand, x is greater than negative 1. We're going to come to negative 1. We're using a parenthesis. It's going to open to the right. And shade. Or x is less than or equal to negative 3. We're going to come to the end point of negative 3 for this interval, and we're going to use a bracket because the equal sign is attached, and the wings of the bracket are going to have to project to the left. We'll shade everything to the left. The graph. Interval notation. I'm going to get my U right here. Bring down that bracket. Parenthesis. The largest value of this interval, negative 3. The smallest, negative infinity. This one, parenthesis to begin, parenthesis to end. Smallest value of this interval, negative 1. Largest, positive infinity. Look at the graphs. That's that typical little look that we will see. Will you always see that? No, but most of the time you will. They're going apart from one another. Okay, now let's see if maybe number 3 is just a trifle different. It seems like somewhere down here, if I copied it down right, there's just something a little bit different somewhere here. Is greater than or equal to 3. 2x plus 5 is greater than or equal to 3, or 2x plus 3 is less than 3. Let's go to him. Negative 5. Negative 5. 2x is greater than or equal to negative 2. Over 2. Over 2. X is greater than or equal to negative 1. Let me bring down that or. Let's go over here. 2x plus 3 is less than 0. Negative 3. Negative 3. 2x is less than 0. Over 2. Over 2. Or x is less than 0. Interesting situation right here as we do it. Let's take a look at the graph. I'm going to definitively put a 0, and then I'm going to open up that negative 1 and put it down right about there, so it kind of gives us a little bit of space. Now let's cater to the look of this graph. This portion says x is greater than or equal to negative 1. That would be this. The bracket would begin at negative 1 and open to the right, and we would shade. Or x is less than 0. Now, ordinarily for x is less than 0, there would be a parenthesis there. That's what that ordinarily would be. I'll just kind of put it lightly just for a moment. But it's going to be trumped. But I'm just going to put it there for just a moment, just so that you can kind of see that if we were just looking at him, he would need to be a parenthesis, and it's got to be less than 0. So that would mean it would project to the left, and it would pick up all of these. Well, folks, as you can see, the entire number line is graphed. The entire number line is graphed. So actually, the graph for this disjunction is the entire number line darkened without the bracket and without the parenthesis. Because all of the values that are less than 0 are going to pick up that negative 1, so we really don't need that bracket there, and we don't need the parenthesis. So let me just do a little bit of erasing. And there's the graph. And actually, the more simplified way of writing your solution is not so much that. That's what we got when we solved it. But now that the graph is there, the solution is really and to show the all real numbers in interval notation, it is a parenthesis. It ends with a parenthesis. It's the negative infinity, comma, positive infinity. We'll need him, and we'll need the graph. This already speaks to all real numbers. You don't necessarily have to write it down, but I did. That is one of the unique looking problems that deals with a disjunction. It's not going apart. It's the entire number line. Wanted to show that. One last one before we end 4-2. 16 minus 3x is greater than or equal to negative 8, or 13 minus x is greater than 4x plus 3. Let's go to this puppy right here. Get rid of that 16. Negative 16, negative 16. Negative 3x is greater than or equal to a negative 24. We're going to have to divide by a negative, so we're going to have to reverse. Negative 3x divided by negative 3. Reverse. From greater than or equal to is less than or equal to negative 24 divided by negative 3. X is less than or equal to 8. Or we have variable terms on both sides. I want the variable terms on the left. Negative 4x. Negative 4x. And folks, I hope that you'll allow me to do this. You should feel comfortable with what I'm about to do. If I'm going to put my variable terms on the left, then my constant terms have to move to the right. 13 has to move to the right. I'm going to do it on the same line. Negative 13, negative 13. The line. Negative 1x coupled with a negative 4x, a negative 5x, is greater than negative 10. We're going to have to divide by a negative. Reverse. Negative 5x divided by negative 5. Reverse 2 is less than negative 10 divided by negative 5. Or x is less than 2. Another interesting situation here. Look at the overall two pieces of the solution. The inequality symbols, no, they're not exactly the same, but the inequality part of both symbols are moving in the same direction. They both are is less than. So that's going to let us know that when we come to our graph, the graphs are not going to go apart from one another. They're just going to be moving in one direction. So I'm just going to kind of leave that there for a moment. Let's go to the graph. And let's stick the prime numbers on there that we need. We've got a 0. We're going to take it to 2. And we're going to take it out to 8. On the one hand, x is able to be less than or equal to 8. That's this, a bracket opening less than in the same direction as that. And we'll pick up all of these real numbers to infinity in a negative direction. Or x is less than 2. Well, x is less than 2 would ordinarily be this. It projects less than, and it moves infinitely in a negative direction. Folks, this portion of the graph that begins with the endpoint of positive 8, since it's moving in the same direction, it is picking up positive 2. So we no longer put that parenthesis there, because this bracket emanating right here, as we pick up all of the points, it's picking up the point 2. Not because of him, but because of him. This portion of the graph is trumping him. There is no parenthesis there. There is the graph. And now before we go to the interval notation, we want to come up and actually simplify this answer a bit. The actual answer is this. It's picking up him. It's picking up him. That's actually our solution, because it's equivalent to the graph. The interval, square bracket, parenthesis, negative infinity, the larger value 8, done. Those are disjunctions. But I'm here to tell you, in most cases, the graph will go apart. But I wanted to show the unique types of situations that we had. We'll be moving into 4.3. You take care for right now. Bye.